So let's consider this new kind of special curve called an ellipse, which is just an oval shape, but it's a special kind of oval shape. I've already asked you to watch some of those YouTube videos where people draw ellipses using a piece of string. And what we're going to try to do here is we're going to try to get from that string drawing of an ellipse to an equation in x and y. We're not actually going to do any problems in this video, so if you'd like to skip it, it's fine. But if you want to understand where the equation of the ellipse comes from, that's really what this video is all about. So let's get back to that idea of how you saw an ellipse drawn using a piece of string. The string was tacked down at 2 points that I've labeled here, F and F prime, and then I'm just going to sort of draw in red what I would call the piece of string stretched out. And so you have to watch one of those videos of someone drawing an ellipse to get this point of where the string comes from. And what we're going to do is we're going to take this string drawing now and think about it in terms of the technical definition of an ellipse, because an ellipse is an oval that has a very special property about it. An ellipse is the curve formed by all points in the plane, the sum of whose distances from two fixed points is constant. Now, let's try to translate this into everyday language. The two fixed points are the F and the F prime point. I call those the foci. Foci is plural, so that the singular is focus, and F stands for focus. And so our F and our F prime, since we have two of them, we call those two foci. All right. So so the two fixed points are the two foci, and the constant that we're talking about here, think of that as the length of the string. So we can stretch it out over here, down here, but any point that we get on that ellipse, if you add this length plus this length, so the distance to one focus plus the distance to the other focus, you're always going to get the same amount, which is equal to the total length of the string. Now, in order to start moving toward an equation, we're going to talk about some parts of the ellipse and give these parts some names. The line that we draw from one end of the ellipse to the other that passes through the two foci is called the major axis. And at the halfway point of the major axis is a point we call the center of the ellipse, and I think you can see why we call it the center. Perpendicular to that major axis, so making a right angle with the major axis going up and down, is another line we call the minor axis. And the minor axis is shorter than the major axis. And at the end of the major axis, so this point here and this point here, these 2 points at the end that actually lie on the ellipse, we're going to call each one a vertex. And our textbook likes to give a name to these 2 points at the end of the minor axis. They call them a covertex. So it's just on the shorter of the two axes is the covertex. And F, again, is a focus. And this F prime is also a focus of the ellipse. Now we're also going to introduce some constants here in these pictures that we draw. I'm going to call the distance from the center all the way out to a vertex. I'm going to call that length A. From the center up to the covertex at the top, I'm going to call that B. And then the distance from a focus to the center, I'm going to call that C. Let's just make a note of these here. Since A is the distance from the center to the vertex, that's actually 1/2 the major axis length. And likewise, B is 1/2 of the minor axis. C is distance from a focus to the center. Either one come out the same. Okay, now I want to continue on another picture here. I want to think a little bit about that string again. Now remember, we could take the string and when we stretch it out, it's tied down to one focus. We can stretch it out to a point on the ellipse, and then it's tied down to the other focus. But there's also one possible position of the string would be to start here at one focus, and I can go right to a vertex on the side, and then I'm exaggerating this because it would really overlap a little bit, and then the string would stretch back to the other focus. And what I want to see from this is that we can interpret this length of string in a slightly different way, because it starts at the F prime focus, goes all the way to the end, this vertex of the ellipse, and then doubles back on itself. But this little piece where it doubles back over itself is the same as this distance over here from the F prime focus to the vertex. So the total length of string, you should be able to convince yourself, that's equal to the length of the major axis. And since half of the major axis we're calling A, the total length of the major axis is 2A, two of those. Another picture I want to draw here is, again, I'm just going back to my ellipse with two foci labeled. The major axis is drawn. The minor axis is drawn. I want to imagine the string in this position. So it's that same length of string going from one focus up to this covertex back to the other focus. Because the length of the string is 2A, when the string is stretched out in this position, this piece and this other piece here have to have exactly the same length. There's certain congruence in this picture here, certain symmetry. And since the total length of the string is 2A, this is A, and this is also A here. Now we've already labeled half the minor axis as B, and this distance is C from either focus to the center. We know we have a right angle here, so we actually have a right triangle in our picture with legs C and B and hypotenuse A. So by the Pythagorean theorem, we know that A squared is always equal to B squared plus C squared. And notice though that the hypotenuse is A, so often in geometry classes we tend to call the hypotenuse C. That's not the case here. A is the hypotenuse, C and B are the legs. And this form of the Pythagorean theorem, in this ellipse situation, we like to isolate C squared. So I'm going to leave A squared where it is. I'm going to subtract B squared from both sides, and then that difference will be equal to C squared. This little equation we're going to use along the way, this A squared minus B squared equals C squared. We'll refer to that later. And just one more, one comment I'm kind of throwing in here, just It's not really connected to anything else, but I have this tendency to draw the same ellipse over and over again on my handout. And actually, ellipses can come out in a lot of different shapes depending on how far apart the foci are. If the foci are far apart from each other, an ellipse will look very elongated, can look enormously elongated, all right? But if the foci are close together, the ellipse is going to have a shape that's almost circular. In fact, you almost can't even tell the difference between an ellipse of that kind and a circle. And then an interesting thought is if the foci coincide, then so if f and f prime are at the same point, the curve you're going to trace out is an exact circle. So in a certain sense, a circle can be thought of as a special case of an ellipse where the two foci coincide at the center. Okay. Now what we're going to do is we're going to try to see where the equation of an ellipse comes from right now. And to get an equation, we have to introduce an xy coordinate grid. So I'm going to put the center of the ellipse at the origin at 0, 0 on my graph grid. I'm going to put the major axis on the x-axis and the minor axis on the y-axis. So the two foci, f and f prime, are both going to appear on the x-axis here. And because c is the distance from the center to a focus, I know these coordinates are going to be c0 and negative c0 for the two foci. And what else do I want to label? I'm going to label my vertices. Now, we already talked about what the length A was the distance from the center out to a vertex. So this vertex in a coordinate system, A will be its x-coordinate, y-coordinate is 0. At this point, we'll be at negative a0. And B is half the length of the minor axis, so these y-intercepts we know will be 0, b, and 0, negative b. And what else do I want to label here? I just want to think, so what we're going to do is we're going to think of xy could be any point on the ellipse. Right? So I'm just going to pick one. Look right here, xy, a point on the ellipse. And here's my piece of string, right? Stretched out. Because we know this distance plus this other red distance, length, they have to add up to the length of the string. Let's actually write out that idea. The length of the string is going to equal, let's see, this distance right here. So the distance from negative c0, the one focus, to my point xy, plus we have our other part of the string over here, and that length is the distance from c0 to xy. Now the length of the string we just said a moment ago on the previous page, we know that's got to equal 2a. 2a is the length of the major axis. And now I'm just going to write out what these distances are using our distance formula. So the square root of x minus a negative c squared plus y minus 0 squareds. So I'm plugging these coordinates into the distance formula, plus I'm going to have another square root. x minus c squared plus y minus 0 squared. And I have a lot of symbols there. And what I'm going to do is, all right, yes, just say that there's lots of steps. I'm not going to write all the steps, but I do have the steps posted online on my handout of Intro to the Ellipse. So that the handout that's posted online looks sort of like so. And we basically just worked our way through the first page of that handout, talking about it. Really, I just broke it down into everyday language, the first page. And we've gotten to the second page of that handout. There's our distances written out. And on the third page of that handout are all the calculations, all the algebra, all the steps involved in getting from what we just wrote down to the following form: x squared over a squared plus y squared over a squared minus c squared equals 1. So basically it just involves squaring both sides a lot, combining like terms, subtracting the same thing from both sides every once in a while. And again, it's spelled out in detail on page 3 of that extra handout that's posted, and it is a lot of messy steps. And now we get to this point, and now I'm going to take it one step further, because we had a relationship that we just talked about: a squared minus b squared equals c squared. Let me just write this on the side here: a squared minus b squared equals c squared. Now I'm going to change this equation. I'm going to interchange the b squared and the c squared. I'm going to leave a squared where it is. I'm going to subtract c squared from both sides, and I'm going to add b squared to both sides. So this is actually an equivalent form: a squared minus c squared equals b squared, which means right there I can replace the a squared minus c squared with b squared. So I get x squared over a squared plus y squared over b squared equals 1, and that's called the standard form of the equation of an ellipse. So my goal was to try in this video to get from the string description of an ellipse to this this form of the equation. And there's just one more thing a little bit more I want to say. This form of the equation depended on us having an ellipse that was had its major axis on the x-axis. So what happens if we have our major axis on the y-axis? Well, there isn't that much that's different. We're just gonna we are going to label the y-axis vertices as 0a, 0 negative a, because we like to use a for the major axis, the longer of the two. So the x-intercepts would be b0 and negative b0. The two foci, since they're on the y-axis, would be at 0c and 0 minus c. And okay, I think the only other thing we've got to say here is, so we write the form of the equation that we're going to get in this way is going to be x squared over b squared plus y squared over a squared equals 1, which looks almost the same as what we came up before. We just got to be aware of the fact that in this situation, the major axis is on the y-axis, and we'll be able to recognize that fairly easily in problems. So I'm ready to stop with this portion where we derived the equation when the major axis was on the x-axis and where the major axis is on the y-axis. And all of this is repeated and summed up on that handwritten handout that's pasted page 1, page 2, page 3. You don't have to read these over unless you really want to. It's got a lot of the nitty-gritty, dirty details involved if you're interested in that. So next video, we'll start doing some problems now.